Good afternoon, all of you. In the previous class, we discussed about second law and third law of thermodynamics, and we discussed even about some conditions of a spontaneous and non-spontaneous reaction. And today we are moving on to our next topic, which is Gibbs energy change and equilibrium. So Gibbs energy, we already spoke about a lot of type of reactions, and from that we spoke about spontaneity, and today we are dealing with equilibrium and Gibbs energy. So till now, what are all things we can predict just with the Gibbs energy of a reaction? So first thing, with the Gibbs energy of a reaction, we can predict the spontaneity of a chemical reaction that we have seen yesterday. So with the equation of Gibbs free energy, from that terms with the enthalpy and with the entropy of a particular reaction, we can predict how the reaction becomes spontaneous or non-spontaneous. Another prediction which we can do is about the useful work that could be extracted from it. So as we know how much is the energy which is required actually for the reaction, which is nothing but the Gibbs energy, so with that we can actually predict the work. And one more law we have learned, that entropy becomes zero when the temperature is zero. So zero work will be done at 0 Kelvin. So with the help of those relations, we can predict the useful work done in a system. So spontaneity and useful work are the predictions which can be done just with the help of Gibbs free energy. These things we have learned in the previous classes. So now moving on to the next section which we are dealing with today. So free energy change in reversible type of reactions. Till now, whatever reactions we considered was irreversible reaction, and equilibrium was not a condition in those reactions. So if a reaction is spontaneous, we will get the products more, and if reaction is not spontaneous, the production of product will be less. All those things we discussed. But now the condition is about a reversible reaction and about equilibrium. So when applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously. This is a known fact for all of you. So a reversible reaction means if we consider this reaction A plus B giving C plus D, and this reaction can also give simultaneously C plus D giving A plus B. So both sides they can work. That's why we tell it's a reversible reaction. At any point of time, it can actually reverse its direction, and hence we call it as a reversible reaction. So when we tell this reaction is in equilibrium, we can tell that one side of the reaction will be equal to the other side, so that A plus B giving C plus D will be equal to C plus D giving A plus B. If that is the case, the concentration of C and D produced will be equal to the concentration of A and B produced. So that is what an equilibrium tells us. So when the free energy used for this side will be equal to the free energy used this side also. So this side and this side, when the free energy use is same, we can tell that delta G will be 0, or the change in free energy will become 0. So we cannot tell that free energy is 0 because reactions are happening anyway. So when reactions are happening, there should be energy, and that particular energy is known as free energy. So free energy is the energy used in a reaction. So as reaction is happening, we cannot tell that free energy is not there. But once this free energy, or towards this direction whatever free energy is there, that is being compensated by the reverse direction free energy. So difference between them becomes 0. As they are same energy used, difference between them is 0. That's why we got this equation. As we are dealing with equilibrium type of reaction, we need to mention one more term here, which is equilibrium constant. So equilibrium constant is a term represented by the letter K, which is equal to the concentration of one side of the reaction by concentration of another side. So this gives us an idea about to what extent the equilibrium is successful, or to what extent we can see the equilibrium existing. So this, if you see, concentration of one side divided by the concentration of another. So when equilibrium is proper, both of them will have equal values and the equilibrium constant value will become 1. Or if one side of the equation dominates, then we will have a different value for k. And now we have to see a relation between k and delta G. So we have an equation 0 or delta G plus RT ln K is equal to 0. This is the relation between delta G and the term K. Here we have the universal gas constant R with temperature T and then log of K. And this is the relation between delta G and K. And if we write this equation in another way, we will get delta G is equal to minus RT ln K. And if we try to convert this ln to log, normal log, then we have delta G is equal to minus 2.303 RT log of K. So this is a very important equation. With this equation, we can find out K and delta G simultaneously. And we have learnt about one more equation of delta G, which was equal to delta G is equal to delta H minus T delta S, the equation which connects the enthalpy and entropy. So this was the primary equation of delta G, and now we got another equation which is delta G is equal to minus RT ln K. So if we compare both these equations, we can write like this. So delta G is equal to delta H minus T delta S is equal to minus RT ln K. So relation between K and delta G again. So now what we are going to do is, we have to see this three equations together, which is the normal reversible chemical equation, value connecting delta G and K, then the equation of K. So with the help of all these three equations, we are going to find out a relation between delta G and K. So here what we are going to do is, we are going to change a term in this equation. So one of the term we are changing, and we will see how the equilibrium constant K will react with that. So in this, what all terms we can change? One is enthalpy, which we can change, another is entropy, which we can change. T is constant there. So enthalpy or entropy. We can change the delta S or entropy, but that is out of the scope of our textbook. So we are not doing that. We are changing the enthalpy and we will see how it reacts with the equilibrium constant. So first we are taking a strongly endothermic reaction. The value for delta H will be large and it will be positive. So for an endothermic reaction, delta H will be highly positive. So when this value becomes highly positive, what will be the change for delta G? We have seen that. So when the temperature is kept constant, when we are changing this as endothermic, it will have a highly positive value. So when this is a positive value, we will get the delta G to be a highly positive value. So positive delta G means the equation is not spontaneous. So that's we can tell this part of the reaction A plus B giving C plus D will not form much, as it will be not spontaneous. So as it is not forming product means the reactant concentration will be more. So hence the concentration of A plus B is much higher than that of C plus D. So hence we will get a bigger value in the denominator. So denominator value is more, then value of K will be much smaller than that of 1. Once we have smaller value here and a bigger value here, then the value of K will be smaller than that of 1 and unlikely to form the product side. That is the first condition. Now we are going to find out in an exothermic reaction where we have the delta RH value is still large but a negative value. So a negative enthalpy reaction without changing temperature means we will get a highly negative delta G. So hence it is a spontaneous reaction and hence A plus B giving C plus D will be forming much. So in that case, the concentration of C and D will be more. So C and D will be more means this part will become bigger and this part will become smaller. Hence, the value of K will be more than 1. It will be much higher than that of 1 and the reaction will be happening to this side more. So that's all about relation of exothermic and endothermic reaction with respect to delta G and K. So it is possible to obtain an estimate of delta G from the measurement of delta H and delta S and calculate K at temperature for economic yields of the product. So this we have done just now. So if we know the value of delta G from delta H and delta S, we can calculate K. So if we know the value of K, we can tell to which side the product is forming or to what extent the product is forming, we can find out. So that's what told here. If we know delta G and K, we can easily find out what or which side the product is forming more or which will yield the product. And this is just opposite of this statement. If K is measured directly, then we can find out the value of delta G. Here we told if we know the value of delta G, we can find out K and yield of the product. Here we are just telling the opposite. If we are measuring K in the laboratory, we can find out delta G at any other temperature given. So with this, we finish our chapter thermodynamics. In this chapter, we have learned a lot of equations like the entropy, internal energy, enthalpy, spontaneity. A lot of equations are there. So if it's better if you make all this equation to a single sheet of paper and study it with comparing to each other. That will help you to learn it easily. So write all the equations into a single sheet of paper and read that carefully. And do try the exercise questions and the example questions given in your textbook. Thank you.